Hello, everyone. This is Riccardo Calaon, and this presentation is about my paper, Momentum Management of a Spacecraft Equipped with the Dual-Gimbal Electric Thruster. Before I get onto it, I would like to acknowledge my co-authors, my fellow PhD student, Leah Kiner, as well as Drs. Cody Allard from LASP and my advisor, Dr. Hans-Peter Schaub. This paper is about the simulation of a very interesting mission design concept, and it features obviously a spacecraft hub, which is actuated by 4 reaction wheels in a pyramid configuration. The spacecraft also has 2 large solar arrays that are gimbaled such that they can rotate about their axis to maximize incidence of sunlight on their surface, therefore ensuring maximum power generation at all times. There is also a dual hinged platform, which is shown on this slide in purple. Such platform has, it can rotate with 2 degrees of freedom with respect to the spacecraft hub. Moreover, there is a solar electric propulsion thruster mounted on such platform. Therefore, the rotation of the platform allows to rotate the direction of the thrust vector with respect to the system. The spacecraft is on an interplanetary heliocentric trajectory. That's why we need the thruster, that is to be able at all times to track a this thrust heliocentric trajectory. Also, solar radiation pressure acts on the system. So the overall purpose of this paper is, can we use the platform or actuate the platform to exploit the thruster and the mobility of the thruster with respect to the spacecraft to perform system momentum management? Before we move on to it, I should just say that all these simulations are run in Basilisk. Basilisk Astrodynamics Simulation Framework is a open source software that is being developed by the ABS lab at CU Boulder, as well as LASP. And it features a C++ core for speed of execution, combined with a Python interface for ease of scriptability. A key component of Basilisk is its modular structure, where each component, each code segment can be added to the simulation very easily with only minimal coupling between code segments. Regardless of that, Basilisk is great at considering all the cross couplings that happen between the elements and therefore producing high fidelity simulations. This is the block diagram that describes all the elements that appear in this simulation. I am only going to talk about the modules that appear in the red box, but just to give a quick overview of everything that is featured in this simulation. So in yellow, we have flight software modules. In blue, we have simulated dynamic components. In green, we have a simulated external torque, the SRP torque. And in orange, we have the inertial thrust direction, which tells us at any point during the simulation in which inertial direction the thruster needs to fire. Specifically, I'm going to talk about the platform reference module, which is the module that computes the tip and tilt angle that describe the rotation angles that we want for the platform, or the rotation angles that describe the rotation of the platform with respect to the spacecraft hub. These rotation angles are passed on to 2 PD controllers, which produce a torque that actuates the platform and thruster assembly. This impacts the spacecraft dynamics in 2 ways. First of all, because the platform and thruster have their own mass, so their motion exchanges torques with the spacecraft hub, and also the change in the direction of the thruster, whereas it's aligned with the spacecraft center of mass or not, can produce forces and torques on the whole system. SRP torque is acting on the system as a whole. And the last thing that I want to emphasize is that we have 2 constraints on the thrust direction. We have the direction along which we want the thruster to fire in body frame coordinates, which is to obtain a torque or a lack of thereof, depending on whether we fire the thruster through the system center of mass. And the thruster also needs to meet an inertial direction. The module that ensures that this is done is the attitude reference generation module, which I'm not going to be talking in this presentation. But this is also this is only to highlight the deeply interconnected nature of all these modules that appear in the simulations that I'm going to show at the end of this presentation. Very quickly, the spacecraft inertia are shown here in the slide. We can see that it's a pretty massive spacecraft. Once again, it features 4 reaction wheels in a pyramid configuration. The inertia of the solar arrays are smaller compared to the spacecraft, but their solar arrays are primarily relevant because of their very large surface area, which causes SRP effects on the spacecraft to be non-negligible. The platform and thruster have negligible mass compared to the system, but the thruster has a specific impulse of 1600 seconds, and it applies a nominal thrust of 0.1 newtons that is assumed to be constant throughout the simulation. Very briefly, solar radiation pressure acting on the system is due to the fact that photons emitted from the sun can impact, or they do impact, surfaces of the system. Solar radiation pressure is here computed using a multifaceted model where only surfaces that are directly impacted by photons are considered. So for each of these surfaces, it is possible to compute a force and a center of pressure. And with all these ingredients, one can compute the resulting torque due to SRP acting on the whole system. So the challenges that we're facing in this simulation are that SRP causes momentum to build up on the reaction wheels, which spin up to hold attitude steady. Also, misalignment between the thrust direction and the system center of mass can also produce a torque on the system that can cause additional momentum buildup. So the question that we're asking ourselves is, can we exploit such torque due to the misalignment with the system center of mass to perform momentum dumping and counteract the effects of solar radiation pressure? In order to see if this is feasible, we need to be able to control the platform the way that we want. So to start defining this problem, we need to define 2 frames. There is a frame M, the mount frame, which moves together with the spacecraft hub, and the platform frame F, which moves together with a platform. There is, in general, an offset between the origin of the F frame and the origin of the mount frame. Moreover, the thruster is expressed in platform frame coordinates, and the application point of the thruster can be in a general point T in the platform. So we cannot, in general terms, assume that the thruster is fired through the origin of the mount frame. Whereas conversely, the location of the center of mass is known with respect to the mount frame. And the most cumbersome constraint is due to the fact that the platform can only perform compliant 2 degree of freedom rotation. Specifically, it can perform a series of tip and tilt rotation about the M1 axis of the mount frame and about the F2 axis of the platform frame. These 2 rotation angles, nu1 and nu2, can be used to compute the direction cosine matrix Fm that describes the rotation of the platform with respect to the mount frame. It is very important to pay attention to the fact that the element on the second row and first column of such matrix has to be 0. If this is not the case, then this DCM is not describing a constraint compliant rotation. Therefore, this DCM does not describe a rotation that is compliant with the 2 degree of freedom gimbal that characterizes this platform. So we want to be able to rotate this platform in order to fire the thruster through the system center of mass, at least in this first. We'll have this as our goal for now. So this is done via a series of 3 consecutive rotations. I will not spend too much time describing these for the sake of time. I will just say that in all these derivations, which are highlighted in the paper, so I would encourage you to read the paper, we define a vector A, which is the offset between the thruster application point and the origin of the mount frame. Vector B is instead the relative position of the system center of mass with respect to the origin of the mount frame. So the first rotation that we are describing here is a rotation that allows to align the thrust vector T or I should say, to make the thrust vector t parallel to vector b. This is done computing the principal rotation angles and vector, phi and e phi. And once these are computed via cross products and dot products, it is possible to compute the DCM, D1M that performs such rotation. It isn't, I want to stress out the fact that we don't know for sure that this first DCM is compliant with the constraint that I was talking before, but we will for now take it as an intermediate result. The second rotation consists in performing an additional rotation to make it such that the thruster is aligned with the center of mass. This is only necessary when vector A is non-zero, so the thruster is fired through a different point with respect to the origin of the mount frame, whereas when vector A collapses to 0, the second rotation is not needed, and this second DCM becomes the identity matrix. Because we are trying to be general, we are providing a solution where there is this offset, and so we need to compute the second DCM through the second principal rotation angle and vector C and EPC. These parameters are a function of the geometry of the problem. I, again, would invite you to read the paper if you want to find the details on how this is done. And this allows us to compute a second DCM, D2, D1, which can be stacked on the previous DCM, D1M, to compute a matrix D2M that describes a rotation that allows to put the thruster through the system center of mass. Once again, this rotation is not constraint compliant. So how do we ensure constraint compliance? We do this by means of a third rotation. If we notice that rotations about the b-axis, as shown in the figure, do not break this result of having the thruster fire through the system center of mass. So we can define a third DCM, which I call D3, D2, which is computed using Gibbs vector, here denoted as Q, which is the function of the principal rotation vector, which is known. It's the unit direction of vector B, multiplied by the tangent of the principal rotation angle theta divided by 2. It is important to notice that theta is not known as this at this stage, so the matrix D3, D2 is a function of an unknown parameter theta. If we multiply this matrix D3, D2 by the matrix D2M that we showed in the first slide, we obtain the final rotation DCM, and we can choose theta such that the final DCM has exactly the shape that we were talking about that ensures that all the constraints are being respected. This can be done by parameterizing all the informations that we know. So we express D2M in terms of its components and E theta in terms of its components. And we obtain this second order equation, or I should say, nonlinear equation that is the product of two second order polynomials. Because the denominator is always positive and the numerator is a second order equation of where the coefficients are functions of known parameters, it is easy to solve for t, with t being the tangent of theta over 2, to obtain the theta angle that ensures that constraints are being respected. Obviously, second order equations do not always have a solution. I would be happy to talk about what happens in this case, but for the sake of time, I will leave it to questions. So once we compute the theta value that we need, we can obtain the final DCM FM that has exactly the shape that we want. It has a 0 in the second row and first column position. And from this DCM, we can compute the two angles, nu1 and nu2, that describe the reference angles for the PD controllers that actuate the platform. Now, we have solved this very interesting problem of rotating this dual-hinged platform to fire the thruster through the center of mass. Now, the question that we're asking ourselves is, what if we want to produce a torque on the system? We can do this in order to dump the momentum accumulated on the wheels. So we do this by firing through a point D, which is obtained as an offset from the system center of mass. This is done, this offset D is computed via a control law. that is derived from a vector delta H, which is the amount of momentum that we want to dump. In this simulations, such amount of momentum coincides with the opposite of the total momentum on the reaction wheels. And assuming that the offset D is perpendicular to the thrust direction vector, we can compute a control law for D, which is obtained as the equation that is highlighted in yellow. I am breezing through the slide, but I just want to highlight the fact that this direction D is obtained via the cross product of the thrust direction vector, the delta H, so the amount of momentum that we want to dump, and all of this is multiplied by a proportional gain kappa, which has the dimensions of a frequency. So what happens if we put all these ingredients together? Here's the numerical results. The first numerical results is, or the first numerical simulation that I'm trying to show highlights the short-term effects on the system. This is a simulation run for only 60 minutes, where we are neglecting SRP effects for now. And also we are not trying to perform any momentum dumping. So the thruster is firing through the system center of mass. And this is just to highlight what happens on a nominal case scenario. We can see in the top left plot that the attitude is being modified in order to track the reference attitude that ensures that all of our requirements are being met. And in the bottom left plot, we see that reaction wheel speeds are initially actuated from 0 to a certain level, and then they decrease back to 0 as the spacecraft reaches its final configuration. Because SRP is not acting in this case, if we were to continue simulating the system, these reaction wheel speeds would most likely remain at 0. Whereas in the plots on the right, we can see that the platform angles are tracking the references computed by the platform reference generation module that I just described. And we can see in the bottom right plot that the offset between the thrust direction and the system center of mass goes from an initial misalignment of 8 degrees to 0. That means we are firing through the center of mass. In this second case, we are showing a longer simulation. We are simulating for a week, and we are, in fact, accounting for the effects of solar radiation pressure. There isn't much to say about the attitude, but obviously we can notice that a lot has changed as far as the reaction wheels. We can see that after the initial actuation due to the attitude maneuver, we can see that over the 7-day window, the reaction wheels are spun up to angular rates of above 2,000 rounds per minute. This is obviously to compensate for the effect of solar radiation pressure acting on the system while also trying to hold the attitude steady. In this case, we are using a proportional gain kappa equal to 0, which means we are again firing the thruster through the system center of mass, as shown in the plot on the top right corner. Whereas there's a new plot in the bottom right corner, which shows the angle between the thruster and the net momentum on the wheels. We can see that this settles at an angle of about 90 degrees. Why is this important? It'll become clear in the next slide, where, in fact, we start from the same assumptions, but we are applying a proportional gain kappa of 10 to the negative 4 hertz. We see that the behavior in this case is significantly different, where in fact we are performing momentum dumping. And we can see that because with the same configuration, we see our reaction wheel speeds over the same 1 week time frame. They're still growing, but they're growing to angular rates that are less than 500 RPMs each. And this makes sense if we look at the offset between the thruster and the center of mass direction, which in this case does not go to 0. It remains fairly small, but we can see that as time increases, the offset with respect to the center of mass is also increasing to compensate for increasing net momentum on the wheels. The bottom right plot, which again shows the offset between the thrust direction and the net momentum is this time going to 0. What does this mean? It means that the thruster and the net momentum, I should say the residual net momentum on the wheels, are aligned with one another. Why is this? Why does this make sense? It makes sense because the control law that we designed for the offset vector D derives from a cross product. So it is not possible to fully control the system to dump the momentum on all three axes. There will be one axis about which we cannot perform momentum dumping. And this is exactly the axis that coincides with the direction of the thrust. This justifies why reaction wheels are still, their speeds are still increasing over time. And this happens because the wheel speeds are increasing such that the resulting net momentum is parallel to the only direction about which we cannot perform momentum dumping. This last slide is only to highlight the fact, the effect that choosing a very large gain has on this control law. What we see here is that the whole simulation is affected by a significant amount of chattering. This is because the control law for D has a proportional, proportional fashion, which is if the gain is too large, the platform is going to bounce back and forward about the 0 position as it's trying to zero this offset without ever being able to converge to 0. I'm showing these simulations to highlight the deeply interconnected nature of all these components. So if the controller cannot converge onto a direction, it means that the platform keeps oscillating back and forth, which means that the thrust direction in body frame coordinates keep changing. And this affects also the attitude reference generation, which causes the attitude to never be able to converge and stabilize, which also has an impact on reaction wheels, which are constantly being actuated to track an attitude reference that can never be tracked. Bottom line is, if we choose a gain that is too large, it becomes impossible for this problem to converge. And this is just to highlight how Basilisk is very good at highlighting all these deeply interconnected phenomena that appear in this in such a complex simulation. So to conclude, it is possible to compute a closed-form solution for the problem involving the reorientation of the platform to fire the thruster through a desired point in the hub, such as the center of mass, but not necessarily the center of mass. In fact, if we choose to fire at an offset with respect to the center of mass, we can dump the momentum that is built on the reaction wheels due to SRP. And the desired control law resembles a proportional type of controller. Its drawbacks are that it is underactuated and that in the current design, it is highly coupled with the system dynamics. And as I was saying, Basilisk is great at emphasizes all these details that would not be obvious if we had made any assumptions on how these different components interact with each other. So that'll be all. If you have any questions, this is how you can reach out to me. And thank you all for your attention. And I wish you a nice rest of your day.